question before you start.
Mhm.
The 5% employer match, is that 5% of what you contribute or 5% of your salary?
Oh, of your salary.
Okay.
Yeah. Okay, that should be there. Almost there. And then just to make sure, do you have tax tables on the back page? Yeah, okay. Just wanted to make sure that you had that.
Yep.
Okay, we'll go ahead and get started then. Chapter 5 is going to focus on statistical reasoning. So this is going to be a intro to statistics. Have any of you ever had a stats class before? No? Okay. That's good for me to know. But essentially what stats is, if my slide will cooperate with me, the science of collecting, organizing, and interpreting data, or using data to describe or summarize something. So basically looking at a situation and figuring out information about what the situation is or what it can tell you. And we do this using a couple of different ideas here. If you wanted to survey everybody, that would be the population. If you wanted just to survey a small collection of people from the population, that's a sample. And the idea with statistics is, can we survey a sample, and can the sample tell us information about the population? Basically, can we put in a little bit of work for the sample in order to describe the entire thing without having to look at the entire thing? Anytime you're dealing with samples, any finding is a statistic. If you're dealing with a population, it's going to be a parameter. So parameter and statistics mean the same thing. It's just what type of audience you have. Always 5 steps in a statistical study. State the goal of the study. Pick a sample. Collect the data from the sample and summarize them. Use what you found in the sample to make conclusions about the population, and then make your conclusions about the population. That is how every statistical study, successful ones at least, follow that format. So an example, each month the US Labor Department surveys 60,000 households to determine characteristics of the workforce. One population parameter of interest is the US unemployment rate, defined as the percentage of people who are unemployed among all of those who are either employed or seeking employment. Describe how the 5 basic steps of a statistical study apply to this. So what would the goal of that be? Or what are they trying to find information about?
People who are trying to find employment, or
Yep, where it has the word interest in it. Parameter of interest is the
U.S. unemployment rate.
U.S. unemployment rate. So the goal of this might be we can calculate the U.S. unemployment rate. The sample is going to be the 60,000 households, right? Once they pick the 60,000 households, then they collect data. They summarize the data, figure out if there's any trends, and then see if it applies to the entire US population based on what they found. Any questions on that example? Now, the idea is that there are many ways of selecting samples. Each of them have their pros and cons. But the idea is that the sample you collect should be representative of the entire population. When you get samples that aren't representative, that's when it leads to bias or systematic issues that exist because of some underlying reason. So some good sampling methods: simple random sample, SRS. Every person in the population has the same chance of being selected. Every sample of the same size is equally likely. So an example would be I put your 3 names in a hat and I draw a name out of the hat. Equal chance of that happening for all 3 of you. And it's random. Then there's a systematic sample. By choosing a random starting point and then selecting every kth member of the population. This would be something like selecting every second person who walks through the door. You have some kind of pattern or system in place to select your sample. Cluster sample is next. This time you're going to split the population into groups that are similar to each other, and then randomly select some of the groups to respond, but ask every member from the groups you select to answer. And the last one is very similar to cluster, called stratified. Still dividing the population into groups. The difference is that instead of selecting some of the groups and asking everybody in the groups that you picked, you're going to pick one or more people from each group and survey only some people from each group. So cluster is everybody from some groups. Stratified is some from every group. Any questions on the good sampling methods? Some bad sampling methods, convenient samples, choosing people or members of the population that are easily accessible. So in other words, if I were going to do that in here, I would pick the people who are closest to me to get answers from. Voluntary response sample. Members of the population choose whether or not they respond. The idea with voluntary responses being bad samples is that typically people who volunteered to be a part of something have some level of interest to some degree. If we have results that differ from the population, that's bias and can result from a variety of different reasons. Bad sampling methods, errors in taking measurements, issues with participants not responding, confusion on question wording are just some of the different things there. Two types of statistical studies: the observational study. Basically, the researcher is just observing the environment without trying to change the environment. So think someone sitting out in the hallway, just taking notes on what they observe, but not interacting with anybody who goes in the hallway. Whereas an experiment, the researcher is trying to make a change to the environment or the participants. Often the researcher controls one or more variables, called the independent variables, and then tries to measure an outcome, which is a dependent variable. So an example, when a random sample of 200 students at Washington University were asked if they had received a parking ticket on campus, 18% of them responded that they had. Is that an observational study or an experiment? What do you think?
So observational.
Yep, observational study. Researchers just trying to figure out information, but not trying to change what's going on. Is the value of 18% a parameter or a statistic?
Stat.
It's a stat because it's from the random sample of 200. The population, in contrast, would be
Parameter.
the parameter. And in terms of Washington University, it would be every student there, not just the 200 that were randomly sampled. Next example, a yoga instructor believes that doing 30 minutes of yoga each day will help reduce a person's stress level. What do you think, observational study or an experiment to show this?
An experiment.
An experiment, just because the yoga instructor will need to control things to actually run the experiment. But getting into more specifics here with experiments, the independent variable and the dependent variable are always in every experiment. Independent variables, think of it as X. Dependent variables, think of it as Y. You're controlling X in order to measure Y. So the researcher manipulates X. It's often called an explanatory variable or factor. Treatments involve the independent variable. You might have a control group that doesn't receive the treatment, but is included for comparison. It will highlight the differences that take place between normal conditions and the group who received the treatment. Dependent variable is observed for changes, and it's called the response variable as a result. So going back to the yoga instructor, we established that we would need an experiment for this, right? What would the independent variable be in that experiment?
The yoga instructor.
The yoga instructor. So they're controlling something. What would the yoga instructor be controlling?
The 30 minutes.
The 30 minutes of yoga. Because that's something that the yoga instructor can implement and control the condition that they all have that amount of instruction. But what would that yoga instructor like to measure?
The person's stress level.
The person's stress level. Yep. Do you think a control group is needed?
Yes.
Yes, I'd agree with that. Might be good to have a group of people who don't receive the treatment compare results to the group who did receive treatment and see what the differences are. Other things that can show up in experiments, placebo. Has anyone ever heard of the placebo effect? Yeah. Essentially, you think you're getting the treatment, but you're not. Often given to the control group in medical studies. It occurs when patients improve simply because they believe they're getting the treatment. Often experiments involve blinding of some kind. Essentially, you're not being informed whether or not you are in the control group or not. They do this because if you knew ahead of time, it might lead to bias in the data. There's single blind where the participant doesn't know if they're in the control group or not. Double blind is when neither the person running the experiment nor the participants know which group they're in, to keep it totally random. If you're reading the textbook, you might see the term anonymous instead of blind. So basically, single is anonymous at the participant level. Double anonymous means anonymous everywhere. But not everything in life is that simple. There's often a confounding variable. Oftentimes, there's more than one reason why a change occurs. And it can often lead to compounding effects. If you know what the variables are, you can hold them constant, but you may not always know what your confounding variables are. Example, researcher would like to know if taking vitamin C helps to prevent colds. Observational study or experiment?
How do you experiment?
Experiment. The independent variable, or the X value, would be
That's all I have.
it's all good. Vitamin C, whether or not they take the vitamin C. The dependent variable, or what they want to measure.
Would it be how much vitamin C they would take?
Close. What's the goal of taking the vitamin C in this case? To prevent colds. So dependent variable would be how much it affects whether or not someone gets a cold. So what would the treatments be?
Doses of vitamin C.
Yep, doses of vitamin C. Single or double blind? Basically, it doesn't matter whether or not the researcher knows who gets vitamin C and who doesn't. Mm-hmm. Yep, I'd say single. Just because they want to look at the differences between not having vitamin C and having vitamin C. Another example, what's the best insect repellent? Say we test two popular brands of repellent, often repel, to see which one will result in fewer insect bites than the other. So what are we controlling here for the independent variable?
Is it the repellent?
Mm-hmm. Yep, the brand of repellent. The dependent variable, or what they're measuring.
Would it be how much insect bites
Mhm.
someone gets from either brand?
So they're met.
No repellent.
What's that?
How many insect bites somebody gets whenever they have no repellent on?
Mm-hmm. For the control group, or if they do get the repellent, how many they would get with the repellent too. So the treatments would be the repellents, right? What are some other things that could throw off the data in that experiment.
Someone might not put the same amount. Like they might not put it all over their body. I don't know.
So different amounts of the repellent.
Reaction to the repellent.
Reaction to the repellent. Mhm. And there are some other ones that would work too. Common one if we looked outside today versus, say, 2 weeks ago. Weather could be a big deal with that. Temperature could be a big deal too. Should we use a control group?
Yes.
Yep. And why?
Because you need to have something to base your results off of.
Yeah. Because there has to be some kind of comparison for the ones who didn't have the repellent versus the ones who did.
I have a question.
Yeah.
On here for part four, it says to calculate in Excel. What do you want me to do for that? Do you want me to just skip it and move on with the information I have? Or,
I was gonna say, if you want, let's have you do a compound interest calculation instead.
I can try.
It's because with compound interest, we know how much is going into it every month. Say you get 6% compounded monthly,
Okay.
based on how much you're putting in.
Okay.
Okay, thank you.
Okay. Sometimes doing experiments isn't necessarily a safe option or an ethical option. This is where retrospective studies come in, or case control studies. So instead of collecting data, you're going to be using past data. But again, often used when experiments are unethical or impossible. But you cannot conclude a cause-effect relationship between the variables. One of the best experiments that fits this category that I can give you, has anyone in here ever had psychology?
Your class or like have paid a psychologist?
Like the class. No? Okay, have any of you ever heard of Pavlov?
Yes.
Yes?
Yes.
No? Okay. Well, Pavlov was the psychologist back in the 40s and 50s, I believe. And he did a lot of experiments on dogs, particularly classical conditioning. Basically, he would put a treat out for the dog, and he tried to get them to associate by ringing a bell before they would get the treat. And he kept doing this so many times until eventually they would hear the bell and they would expect a treat, even if a treat wasn't there. So he would try to get the dog to salivate before getting the treat. Now, that's a pretty mild example there. But as you could imagine, it didn't stop there. He did all kinds of other experiments with that. Another one that typically comes up under the unethical category, during World War II, Germany, they did a lot of experiments on humans at that time. Obviously not something that we would want to promote now, but that's falls under that category. But here's a more current example. Do seatbelts save lives? Probably shouldn't be going out there asking people not to wear seatbelts when driving, because bad things can happen with that. Instead, you look at past data of what happens when people don't wear seatbelts. Does anyone know how that study would conclude? If you had to guess what the conclusion is?
That seatbelts do save lives.
Exactly. Yep. But you can pair it up with past data where people didn't follow and then they either got injured or lost their life because of it. Any questions so far?
So,
Mhm.
I'm sorry, whenever I'm calculating the 401k, do I use the gross salary or for the listed salary?
You could use the gross salary.
Gross, okay, thank you.
You're welcome. Big thing in stats is being able to draw conclusions, as well as providing how confident you are that your conclusion is correct. So confidence intervals are using sample statistics to estimate the boundaries of the population. Most of the time you'll see 95% confidence intervals. Basically, that means if we were to repeat the experiment over and over again, 95% of the time we would fall within this range, is what that means. A margin of error, or MOE, is the amount that you could be off by. Often reported as statistic plus or minus margin of error. So say I run a statistical study on myself on the average number of pieces of pizza that I eat for dinner. And say the average is 3 plus or minus 2 there at a 95% confidence interval. That means 95% of the time I would be eating between how many pieces of pizza on the low end versus the high end? If it was 3 plus or minus 2, 1 in 5. So average is 3, but margin of error is 2, so it could be 2 down or 2 up. The higher number you see with the confidence interval, the more confident they are. The 3 most common ones are 95%, 99%, and then 99.9%. But it's just different levels of precision with those. So an example here. This is a study of Americans taking a dim view of Trump's plans to expand U.S. territory. And you can look at the data there. But at the very bottom, it says gathered responses from 1,422 adults had a margin of error of about 3% points for all respondents. So that means all of these numbers can go up or down by 3% to account for error. So when you see 29 there, it could be as low as 26. It could be as high as what number?
32.
32. But that's how margins of error work. Are the moves too erratic? Margin of error of plus or minus 3% for adults, plus or minus 5% for the other groups. So again, it's just giving you a range of low end versus high end. If they were going to repeat this experiment with other groups of 1,422 people. This one's dealing with Elon Musk. 2,601 adults, sampling error of plus or minus 2.1% of each of them. Margin of error larger among subgroups. When you see the word sub, does that mean bigger or smaller? Smaller, right? The smaller the group, the more likely you will notice big changes in error. The larger the number, the more close together the error should be. Any questions on anything that you see so far? So the question, what do you believe? Because there's an old saying, there are 3 types of lies. You know what they are? The phrase goes, lies, damn lies, and statistics. Those are the 3 types of lies here. So basically, one is statistics lying to you, and one is it telling you the truth, is what this section is about. Eight guidelines to consider, whether or not it's a good study or whether you should believe it or not. Consider the big picture, consider the source. Do you see any type of bias? Any types of issues with measuring or collecting data? Other issues that could lead to the results? Confusing wording, results presented fairly, and do the conclusions make sense? So an example, in Boulder, Colorado, it announced that 28% of school children were reading below grade level and concluded that methods of teaching needed to be changed. Announcement was based on reading tests on which 28% of Boulder schools children scored below the national average for their grade. Does that data support the conclusion? What do you think? No? I agree.
As I said, it's just one, like it's just text.
Yeah, I agree with you. It doesn't support that. But here's where it gets interesting. Do you think that the average student reads at grade level? Like if we were going to go to another school in the area and go to a random classroom, let's say 9th grade. If we picked an average student out of that room, would they be at a 9th grade reading level? Probably not. As sad as this is to say, most students are at least one grade below grade level. Maybe even more. So 28% scored below the national average, but we don't know if the national average is ninth grade or if it's seventh grade for students who are in ninth grade. We're just comparing them to their peers. We're not comparing them to a standard of some kind. But that's another way of looking at that example there. Another one, the fast diet supplement are compared to the weight losses of a control group who tried to lose weight in other ways. After 8 weeks, the results show that the treatment group lost an average of a half pound more than the control group. Assuming that there are no dangerous side effects, does that conclude that it's a good treatment for people wanting to lose weight? Based on the data. So another way of thinking about this is an extra half a pound noticeable enough to say that it's a good way for people wanting to lose weight? Probably not. We could say there's a slight correlation there just because of that difference existing. But is it noticeable enough? You could go either way on that, I think. But these are the kinds of things that you'll have to look at result-wise from statistics. But oftentimes in stats, it's collecting the data, but the other piece of it is presenting the data, particularly in tables and graph form. Two types of variables, qualitative and quantitative. To summarize the differences, quantitative means a number or how many of something. Qualitative means categories or groups that are not numbers. So if your answers are not numbers, it's qualitative. If you're getting numbers of some kind, it's going to be quantitative. So examples, the brand of shampoo you use, qualitative or quantitative? Qualitative. Amount of money spent on pizza last month. Quantitative, it's a number. Favorite pizza topping. Qualitative, zip code. Quantitative, just because a zip code is going to be a number of some kind. Like I know Du Bois is 15801. The only other one I know is Clearfield, 16830, I think.
Woodlands 16881.
Okay.
I forget what Phillips Spring is.
16866.
Okay.
And that'd be West Decatur, so mine's 16870.
Nice. But the first type of table is a frequency table. Basically, you're listing categories of the variable in one column and then how many times it occurs in the data for the second column. If you have quantitative data with numbers, you might create bins that group the data into categories covering a range. So an example here, going back to the pizza example, you can say number of pieces of pizza eaten, 1, 2, 3, 4, and then figure out how many people would vote for each of those numbers. But if you don't want it to be that specific, maybe you want, say, 1 or 2 pieces. How many people would have 1 or 2? Or how many people would have 3 or 4 pieces? But grouping the values like that into categories is the idea. Bins can also be called classes. But essentially, it's just how you want to split up the categories to collect the data. So an example here, diners at the cafeteria were asked their choice of ice cream. And they got these results. Or employees were asked how many miles one way they commuted to work. 4 people had a one-way trip from 0 to 5 miles, not inclusive. 29 would have been from 5 to 10, 26 from 10 to 15, and so on. I know I usually fall in the 5 to 10 range. Last I checked, I think I'm about 8 miles away from my house for where I work. But I know some of you, I'm willing to bet you're probably in this range, coming from Clearfield and West Decatur and those places. The frequency table sometimes has an additional column called the relative frequency. It's how much percentage-wise of the data falls in that category. To figure that out, just take the total number of times it appears in the table out of the total number of votes or tallies, often displayed in percent form or as a decimal. So an example of this. How many total people responded to that survey?
$115.
115. So the relative frequency for vanilla is 37 over 115. Percentage-wise, that would be 32%. And we can do this for all of the other ones. So if someone wants to calculate those,
chocolate is 27.
27.
Cookies and cream is 21.
21.
Strawberries is 11.
11.
And 6% for Rocky.
6% for Rocky Road. And then just to clarify, 0.32, 0.27, 0.21, 0.11, and 0.06 in decimal form. Now we're going to start talking about different types of graphs. The pie chart, often used for qualitative data or categories. And it's really good at showing what percentage of the whole pie each category takes up in the data. A bar chart, on the other hand, is really good for the actual number of times data shows up. There's a variety of ways to do that, horizontally or vertically. A Pareto chart shows bars vertically in descending order. So think multiple bar graphs together. But pie chart there for favorite Dairy Queen treat. I don't know about you, but I would be in the Blizzard category. Same graph as a bar graph. Pareto chart in descending order. Or if we had multiple categories for each. Other ones that can occur are histograms. Basically, for histograms, think bar graph, but the rectangles all connect. So there's no space in between the rectangles. Time series graph, often used when time is involved. Things like the stock market use time series graphs. Often really good at showing trend lines or the pattern expected over time for a set of data. So that right there is an example of a histogram. So notice the rectangles are all connected. The only one that's not there is 1, but that's because we didn't have anyone that voted for 1 in that case. Time series graph. So showing a trend of data over time from 1990 all the way to 2022, it looks like. But no matter what type of graph you choose, you're always going to need these pieces. A title or a caption explains what you're showing, and if necessary, where the source is of the data. A vertical scale and title and a horizontal scale and title. That way we know what the dependent variable or vertical one is, what the independent variable and the horizontal variable is talking about. a legend or a key, basically if you have a lot of different pieces. Often these are color coded, and that gives you a quick glance of each category just by looking at it visually. Any questions on any of the different types of graphs or what you need to create a good graph? Okay. Graphics in the media. Oftentimes, when you see things in the media, you're going to see graphs that compare each other. So in other words, think bar charts that are going to have two or more on the same chart to show a comparison between them. And same goes with time series graphs, or really any of the other types of graphs. Comparative bar chart. Each category is represented by a set of bars for being compared. And for this one, you can use relative frequencies if you're trying to make associations between variables, or if you're trying to look at percent differences or percent change from one variable to the next. So an example here of a dual bar chart. What is the absolute difference in all adults who use TikTok in 2023 compared to 2020?
There's a significant increase from 2023, like, there's a lot more people using 2023.
26%.
Yep, this is going to be 26% higher because you're going from 14 to 40%. So an absolute change of 26%. Percent increase, rather. Anytime you see percent increase, you should think new minus old over old, right? Times 100. So the new value in 2023 is let's see, new value 40, right? Minus old value of 14 over an old value of 14 times 100. Which will be whatever 26 over 14 is times 100. So 185.71%. increase. That makes sense because if we were doubling from 14 to 28, that's 100% increase. If we were tripling, 14 times 3 would be 42. That's pretty close to the 40 there. Tripling would mean a 200% increase. So 185.71 seems reasonable for that. Here's an interesting one. Dogs versus cats. Share of pet owners that said they have a dog cat in 2022 by country. Can you state that more people in Germany own cats than in China? Is the question.
Yes.
Yes?
Yes. No,
No?
no, we don't know the populations of each country.
Exactly. Yep. If it was just what percent more, then it would be Germany.
Sorry, for some reason I thought there was a stated, like, we asked 100 people. But no.
That's okay. Yeah, because the idea, you can only compare percentages if they have the same population. But because China and Germany have very different populations, we would need more information in order to say that, is the idea. Any questions about that? Oftentimes, you can see stacked bar charts. So instead of separating the bars out, they're all going to be on top of each other. But you can still break it down into categories. So here's an example of a stacked bar chart. Early votes in 2008 are 31.7, and it's a part of the total votes there. If you wanted to figure out how many votes were not early votes in 2008, what would you have to do?
You'd have to add each, what do you want to call those, sections, colors,
Mhm.
and do the math to, I'm sorry, his hands.
It's okay. But if 31.7 were early votes, we had 131.4 in total. That means about 100 of them were not early votes, right? So it would involve taking the total minus the section in order to get that missing piece there. But that's what you would want to do for the stacked bar charts. Presidential voting, This is done in Excel here for stacked bar chart. Is the headline accurate though? Did early voting double in 2020? We'll say compared to 2016.
Yes, but we're missing the number of total votes.
Yep, so early voting from 2016 to 2020 doubled. But we don't know how that is in relation to the total votes. But if you did new minus old over old, you'd actually get 99.15% increase, so almost doubling. But do you notice how we're comparing different things on the same graph? You can do this with time series, comparatively, or stacked. The top line represents total cumulative of all groups when doing this with time series. So prime example here, if landline phones are a dying breed, so this is a stacked time series graph. But the idea is that we can do some different things with this data. What was the percent decrease from 2008 to 2022 for landline phones? So landline phones are that color in 2008. So what percent of people had them? 80. So think old value is 80. The new value in 2022 is 28.7. So if we think new minus old over old times 100,
Is it
65.25. That's really close to what I got. Let's see, 28.7 minus 80 over 80.
Oh, 64.127. I think I put
Yeah.
27.8. 27.
That happens. 64.15%. And then out of curiosity, was there a negative in front of that?
Yeah, I just wasn't sure if we
Okay. So with the negative there, that's just going to tell you direction. So if it's negative, it's going to be a decrease. So then if it was positive, that would mean
Increase.
increase. Then let's see if we can get some other numbers here. In what year did the cell phone only overtake the landline phone? 2016? Seems reasonable, looking at where they intersect. So about 2016. What is the absolute difference in cell phone only compared to landline in 2022? That would be the 70.7 minus the 28.7.
42.
Yep, 42. %42 is the absolute difference. And then the last question, what is the percent difference in cell phone only compared to landlines in 2022? So landlines in this would be considered old. So then that means cell phones would be considered new. One of these days, I'm going to be able to actually spell old on this. So cell phone is going to be new. So cell phone in 2022 is 28.7.
146%.
Let's see, minus the old. Have the numbers flipped around, so 70.7. New minus old of 28.7 over the 28.7, right? Times 100%. Was that 146? Okay, 146. And then if we kept going, 0.34%. Any questions on what you see there? Okay, I think this is a good place to stop for tonight. What do you think? Yeah, that sounds good. We actually accomplished quite a bit tonight with the notes.
This seems to be a little bit of a shorter chapter.
Yeah, it kind of is. The interesting thing, this chapter has a lot of like statistical terms. There's going to be more math behind the stats in chapter 6
Oh, goody.
when we get there. But that'll be for another day.